Hi, my name is Enoch, and today I will be presenting my project of simulating a basketball hoop. My project is all about solving the lack of space to practice basketball skills in Hong Kong and the lack of efficiency in shooting practice routines. As shooting is the most important skill in basketball, having an efficient practice routine is crucial to improving as a player. All basketball practice machines currently on the market aim to retrieve the ball quickly after a shot and deliver it back to the player. For example, one such machine is set up around the hoop. Netting surrounds the hoop and catches every miss and make. The machine then funnels the ball into a launcher set up on the ground, which delivers a pass to the player. However, there are many drawbacks to this machine. Even though it greatly raises the efficiency of practice, it is very inaccessible to many. They are large in size, expensive, and makes sharing a basket very difficult. These machines are also not designed to be moved around, making it only suitable for private, indoor courts. This makes it impossible for recreational players to use, as they do not have the necessary resources to use this machine. My project increases the accessibility and efficiency of shooting practice. With my project, only a narrow corridor is needed to practice shooting. This makes it possible to practice without leaving the comfort of one's home. My device allows practice at home with not much space needed. There is no need to retrieve the ball because there is no rim for the ball to bounce off of. The ball will simply bounce off the wall and its accuracy will be detected by the sensors set up. The sensors used in this project are ultrasonic distance sensors. They emit ultrasonic waves and they measure the time from emitting the wave to receiving the reflection of the wave, and they use that to calculate the distance. This will help me determine how far the ball is from the wall when it passes the height of the rim. I tested the distance sensor to determine its field of view and its detection cone. The detection cone can be modeled by the formula shown here, and the values of my testing are shown to the right. The distance sensor has 4 pins that needs to be connected to the Arduino board. First of all, the VCC needs to be connected to the positive supply voltage. Second of all, the trig pin allows a pulse of ultrasonic waves to be sent when an electrical signal powers it. The echo is the opposite of the trig. It produces an electrical pulse when the sensor receives the reflected ultrasonic waves. And finally, the ground pin needs to be connected to the ground potential of the circuit in the Arduino. To get the reading from a distance sensor, I wrote a function in the Arduino program. This powers the trig pin for 10 microseconds, which sends a pulse of ultrasonic waves from the distance sensor. It then waits for the signal to be picked up, which can be detected through the state of the echo pin. The function then calculates and returns the distance using the elapsed time and the speed of sound. I then had to wire the entire device together. Each distance sensor is wired with 4 wires, as shown in the previous slide. All VCC pins are connected to the V-in pin of the Arduino through the breadboard, while all ground pins are connected to the ground pin of the Arduino also through the breadboard. Each distance sensor then has its echo pin connected to a separate pin on the Arduino. Each sensor on the bottom row also has its trig pin connected to a separate pin on the Arduino. However, due to the lack of pins on the Arduino, as the Arduino only has 11 pins for input and output, the top sensors have to have their trig pins connected to the same Arduino pin. Finally, each LED is connected to its own Arduino pin and grounded through a resistor. This allows each LED to be separately controlled to indicate makes and detected shots. Here is my first prototype. To the bottom right corner is my computer model of overlaying 3 detection cones. These detection cones would cover the entire rim, and it will detect any shot that has a center go through the rim. I assumed that any shot with the ball center inside the rim would be a made shot. During testing, I found that this was too generous and did not account properly for misses that bounced off the rim. To the top right is a picture of my first prototype, which had 3 sensors lined up side by side on a ruler spaced apart. My second prototype accounted for the ball bouncing off the rim. Here are some rules I used to determine the accuracy of a shot. I then used a computer program to simulate the area of the virtual rim that will be counted as a made shot. Here is the result of the computer simulation. The black line at the top is the backboard, the black circle is the rim, the green circle is the area of the rim that could be a swish, and the solid red areas are where the shot would be a miss. The area surrounded by blue spots is the area that the ball would bounce off the rim and into the basket. Some of the blue area overlaps the green area because the angle that the ball goes into the basket does not allow a swish. Therefore, any green area with blue surrounding it will not be a swish, but a made shot off the rim. I then overlaid 3 detection cones, indicated by the black trapezoids, to cover the determined area. A detection within these 3 cones will indicate a made shot. I also added 3 additional distance sensors above the original 3 in order to confirm that a shot has been detected. The light gray trapezoids are the detection cones for the upper distance sensors. A detection from those sensors indicate a detected shot. This is necessary to ensure that a shot is detected before a shot made is counted. Otherwise, anything flying across may count as a made shot. I then wrote a program on the Arduino for the device to operate with. First of all, the top line of sensors repeatedly detect distance. If an object is sensed within 1 meter of any of the top line of sensors, it activates the bottom row of sensors for 0.2 seconds and turns on the left LED, indicating a detected shot. Within that 0.2 seconds, if the bottom row of sensors detect an object within the area of the virtual rim, it will turn on the right LED, which indicates a made shot. The reason for the time frame of 0.2 seconds is that it is the maximum time that a ball would need to travel from the top line of sensors to the bottom line of sensors. Here is the structure of the entire device. For each distance sensor, there is a 3D printed sensor holder to protect the sensor and its pins from any flying basketballs. There are also 3D printed spacers to keep the 2 lines of sensors apart. The 2 lines of sensors are placed on rulers to space the sensors properly. The box on the top holds the Arduino, the breadboard, and the battery pack to keep everything in one place. I also created a 3D printed stand for demonstration purposes, but that will not be in use of the product itself. To test the device, I printed out a real size rim and I threw the ball at the rim repeatedly to see if the device determined the accuracy correctly. Prototype 1 was too generous with the shot accuracy, which led me to create Prototype 2. However, Prototype 2 successfully simulated a basketball rim. Therefore, it became my final prototype. My device successfully creates a virtual rim with sensors and could be a useful practice tool, but it must be made more consumer-friendly if it's intended as a product on the market. Of course, nothing is perfect. If I had more time, I would take this project further and make it more user-friendly. Since my project is a product aimed towards basketball players, I can make the design more visually appealing. More specifically, I could add a visible rim in 2D so that the shooter could visualize a rim to aim at. I could also combine or wrap the wires to make them neater, and possibly use soldering and a PCB to replace the breadboard and many wires. This would make my product more user-friendly and visually appealing. Doing this would make my product viable on the market, allowing it to help basketball players in Hong Kong and around the world that are strapped by a lack of a good practice environment. Another improvement to my design would be to replace the ultrasonic distance sensors with time of flight distance sensors. Since time of flight distance sensors are more accurate and can take more frequent readings, they will allow me to determine the velocity and position of the ball with more accuracy. In turn, this will enable me to detect the angle of entry of the basketball and make more accurate calculations of the ball bouncing off the rim. The speed and angle of entry of the ball are both useful analytics for a shooter, as it allows them to see their consistency outside of makes and misses. Finally, I could add a segmented display or monitor to show the results of a practice session and display the analytics for each shot to the shooter. This is an improvement from only indicating whether each individual shot was made or missed using 2 LEDs. In conclusion, my project was successful, but there are multiple ways I can take this project further with more time. From learning how to use and the principle behind the distance sensor, to making an entire structure and device with multiple distance sensors overlaying their detection cones, this project has been a journey. Through much testing and failure, I have learned the importance of creating more prototypes and improving through every iteration of my design. The engineering process has propelled my project, and I am thankful for the opportunity to put this process into use. I hope to continue to apply the engineering process to future projects and use these new acquired skills to help others. Thank you for listening.